little baby.
Well, the next activity this afternoon is a special lecture on the Poincaré Conjecture by John Morgan. So Professor Morgan is a topologist who's always had an interest in the interface between topology and other subjects, algebraic geometry, gauge theory, theoretical physics, and so it's no surprise that now he's very interested in Ricci flow and its impact on topology. So, as you may well know, he and Gang Tian produced an extensive exposition of the ideas of Perelman in solving the Poincaré conjecture. Today, I believe he's going to offer a general view of the Poincaré conjecture for all of us here. So, Professor Morgan.
Thank you, Nigel. It's a great pleasure for me to speak to you today about a stupendous achievement in mathematics. Gregory Perelman has solved the Poincaré conjecture. The posing of this 100-year-old problem marked, in my view, the founding of topology as an independent discipline. Since its posing, the problem has been studied, generalized, related problems have been solved. It has been linked in one way or another to most of the progress in topology in the last 100 years. Now, while related problems have been solved, the original conjecture, as posed by Poincaré, stood untouched, resisting all attacks. Before Perelman's work, many viewed it as a siren song, for many boats had foundered on the rocks trying to reach it. There have been innumerable proposed proofs, innumerable proposed counterexamples, but none withstood scrutiny. Solving the Poincaré conjecture is a signal achievement for Perelman, but it is also a signal achievement for mathematics, for it is a measure of how far our understanding of the subject has advanced in the last 100 years. Perelman has seen far, but to do so, he stood on the shoulders of giants. One giant in particular stands out. He is Richard Hamilton, who addressed this conference on Tuesday about his work and its relationship to Perelman's. Over a period of 25 years, Hamilton painstakingly built the solid and elaborate foundation upon which Perelman constructed the edifice of his proof. Without Hamilton's work, Perelman's would not have been possible. Today, I will begin by giving you a sense of the importance, centrality, and depth of the Poincaré conjecture. Then I will introduce you to surfaces and three-dimensional spaces, we call them manifolds, and tell you some of the ways topologists think about these spaces. Next, I will formulate and explain the statement of the Poincaré conjecture. Then I will shift subjects and give you a brief introduction to differential geometry, which is the field of mathematics out of which the proof of this topological problem comes. I'll talk about Hamilton's Ricci flow equation and then briefly describe Perelman's insights. I will not be able to give you anything but a superficial, metaphorical impression of the mathematical arguments. For those interested in more details, I will give you links to over 1,000 pages now available on the web where you can learn more in detail. My goal here is to explain the significance of the conjecture and its statement. Let me begin with the role of problems in general in mathematics. So from the beginning of the subject, there have always been problems, and they've always played a significant role. In fact, during the 18th and 19th centuries, mathematicians pose each other problems, often giving 6 weeks, 2 months, half a year for solutions, and learned societies often posed mathematical problems to the general public and offered prizes for their solutions. Oops. The nature of problems in mathematics, I believe, changed with Hilbert's talk at the International Congress of Mathematics in Paris in 1900. There he proposed a list of 23 problems covering a broad range of mathematical fields. These problems were of a different character than the ones that had been posed in earlier times, for Hilbert viewed them as the central problems of mathematics as he saw it in his day, and he thought the study of these problems and their solutions would lead the field forward. And indeed, he was quite prescient, for much of the progress in 20th century mathematics has revolved around these questions, and to solve one is to be recorded in the Mathematics Hall of Fame. In 2000, following the tradition established by Hilbert, the Clay Mathematical Institute identified 7 important and central problems in mathematics. Things had changed a little bit in the intervening 100 years. There was no Hilbert, so Clay leaned on the support of a committee of leading mathematicians in order to choose these problems. And we're a much more materialistic society, so they offered $1 million per problem for the solutions. What makes a good mathematical problem? Let me quote to you from what Hilbert said in his address to the Congress in 1900. It comes out a little funny in English because I believe it must be a translation from the German, but nevertheless, I should still more demand for a mathematical problem if it is to be perfect. For what is clear and easily comprehended attracts, the complicated repels us. Moreover, a mathematical problem should be difficult in order to entice us, yet not completely inaccessible, lest it mock our efforts. It should be to us a signpost on the tortuous paths to hidden truths, ultimately rewarding us by the pleasure of the successful solution. That's what we're celebrating today, the pleasure for all of us of the successful solution. So I think what Hilbert was trying to say was at least these things, among others. Studying a good problem stimulates a tremendous amount of mathematical research. Some of it's directly on the problem. Sometimes it simply spawns research in related areas. You never know where studying a problem will lead you. I guess you start hoping it will lead you to the solution, but wherever it leads you, you follow. Problems become more and more famous as they resist more and more different attempts over time at their solution. And the famous and old problems are used as standards for testing new ideas. As a new idea enters mathematics, one way to test its power and relevance is to try to use it to solve old problems, and that's the toughest test, and if it passes that test, it will be ensconced as important in the subject. So now let's turn to our particular problem, Poincaré Conjecture. It was formulated in 1904 by Henri Poincaré, so it's a little too young to have made Hilbert's list, 4 years too young. The problem proposed a characterization of the simplest of all three-dimensional shapes, that is, the three-dimensional sphere. And I'll come back in a few minutes and try to explain to you how to think about, first of all, what the three-dimensional sphere is and how to think about it. It has been attacked in the intervening 100 years by direct topological means. So it was a problem in topology. The hypotheses are topological. The conclusion is topological. It's natural to try to solve it in the terms in which it's posed by direct topological means, and there was no success. Nobody has managed to do that. But there was a lot of effort put into it. Studying the Poincaré conjecture did, however, lead to many advances in the study of other three-dimensional spaces by a variety of workers over a period of about 30 or 40 years. We learned a lot about three-dimensional spaces, but none of it was relevant to the Poincaré conjecture, which stood there as a beacon untouched by any of the new methods. And one of the most revolutionary ideas in all of topology, as far as I'm concerned, Stephen Smale realized in 1960 that, in fact, one could formulate the Poincaré conjecture in all dimensions. That wasn't too revolutionary. But that, in fact, it was easier to solve in higher dimensions. And he, in fact, went on to solve it in dimensions 5 and higher. And for that, he won the Fields Medal. I believe that Poincaré's idea was the following simple, intuitive, naive idea. We understand surfaces, two-dimensional spaces. They were understood by the end of the 19th century. Clearly, the next thing to try to do is understand three-dimensional spaces. He wrote a long paper about them, and at the end of that paper he said, well, we've achieved a lot, but this leaves one remaining question, and then he posed the Poincaré conjecture. Surely, in the intervening years, people thought, well, if we can't solve this problem in dimension 3, there's no hope in dimension 4, 5, 6, and on. This problem is just going to get more and more complicated. We have less and less intuition about what these higher dimensional spaces look like. And Smale's revolutionary idea was, to the contrary, it becomes much easier in high dimensions. And slightly earlier, in 1956, Milnor provided counterexamples to a closely related problem in dimensions 7 and higher. He told me that when he first discovered this, he thought he'd found a counterexample to the higher dimensional Poincaré conjecture, but it turned out in the end he had a counterexample to a closely related conjecture, and for this work he also won the Fields Medal. In about 1982, Mike Friedman, and an incredibly powerful tour de force, took the ideas that worked in higher dimensions and managed to squeeze them down so that they worked in dimension 4 at the expense of crinkling the space in infinite complexity. But he did solve the formulation of the conjecture in dimension 4, and for that he won a Fields Medal. At almost exactly the same time, a young English topologist, a student of Nigel Hitchen, whom he later traded to Michael Atiyah for future draft choices, Simon Donaldson, solved a problem very closely related to what Friedman was doing, but not for crinkly spaces, but for nice, smooth spaces, spaces on which you can do calculus, write down derivatives, and do differential equations. And the contrast between what Friedman proved for crinkled spaces and what Donaldson proved for smooth spaces showed us that 4 dimensions was like no other dimension. The divergence between these two seemingly very close notions were, in fact, totally different in dimension 4. In fact, one had always believed until Milnor's result that there was no difference between the two, and certainly that's how Poincaré thought of things. He was lucky. In dimension 3, there is no difference. Moving the story along, in about 1980, Thurston, working on hyperbolic three-dimensional spaces, proposed a generalization of the Poincaré conjecture to a conjecture about all three-dimensional spaces. And for that, well, actually not for that, but because he did that, he won the Fields Medal. His conjecture is different from Poincaré's conjecture in 2 essential ways. First of all, as I've already said, it covers all three-dimensional spaces, whereas the Poincaré conjecture, if it's true, only covers one, the simplest. And secondly, the way Thurston formulated his conjecture was that the three-dimensional spaces had nice geometries. And this suggested the idea that, as we'll see later, was picked up by Richard Hamilton, that one could study these three-dimensional questions using geometric methods rather than purely topological methods, analytic and geometric methods. And here we are today. 3 years ago, Perelman solved the Poincaré conjecture, and as we now know, he has a Fields Medal for it. When I first prepared this talk 2 weeks ago, I had 2 question marks next to the Fields Medal, but I got to erase them, for which I'm quite happy. So what is the method of solution that I've alluded to? Let me say just a couple of more words about it, and we will cycle back later to a little more detailed description. Perelman's solution used differential geometry and partial differential equations to attack this problem that in its formulation is purely topological. He used an equation, an evolution equation called the Ricci flow equation for Riemannian metrics, and I'll try to talk both about what a Riemannian metric is and what the Ricci flow equation is in a few minutes. This equation was introduced by Richard Hamilton, who went on to develop a rich theory about the solutions of this equation and to lay out a program for attacking the Poincaré conjecture and, according to Richard, with crucial input from Yao, Thurston's more general geometrization conjecture. All right, well, now it's time to turn to the topology. I have to tell you a little bit about the topological spaces that we are thinking about. And we'll follow Poincaré and work by analogy. Two-dimensional spaces are easier to understand. We can see them for the most part. And our intuition is guided by this very concrete present representation we have of them. Three-dimensional spaces are harder, and we have to argue by analogy. So I will go back and forth for a few minutes between two-dimensional and three-dimensional spaces. So let's start with the simplest one, the two-sphere. I've given you two representations of the two-sphere. On the right, I've written its mathematical equation, and on the left, I got a picture of a two-sphere. What I think of as a two-sphere, my wife says it looks nothing like a two-sphere. You can judge for yourself. The one thing I want to emphasize at this point, because it's often a point of confusion for non-mathematicians, when we say the two-sphere, we mean the surface of the ball. The ball would be the solid thing, and it's a three-dimensional object, but its surface, which we see sitting here in space, which we see over here, talking about the surface itself, that's a two-dimensional sphere. That is the two-dimensional sphere. Now, there are other surfaces, and these are understood to be the surface, not the solid object. We have the often called the surface of the donut, or a torus. We have a two-hole torus. And then here I have a picture. I believe this is probably a 12-hole torus. You see around the sides, you see 6 handles, each one with a hole. Then you see 3 in front, and I believe we're to imagine 3 more in back. In fact, this is what all surfaces look like. They look like some multi-holed torus. I have 0 holes as the sphere. Here's a 1-hole torus, a 2-hole torus. You can imagine the intermediate ones. Here's a 12-hole torus. Keeps going. So that's what all these surfaces look like. That's a complete list of them. Now, why are these two-dimensional? They're sitting in three-dimensional space. We look at them. We pick them up. They look three-dimensional. But in fact, they are mathematically two-dimensional because you can describe where you are on one of these surfaces by giving 2 numbers. I'm sure you're quite used to that in the case of the sphere. If you think of the sphere as being the surface of the Earth, if you want to tell somebody where you are, you give latitude and longitude. If you were on the donut, you could give 2 angles. Again, an angle around this way and an angle around that way. It would take 2 angular numbers to specify where you are. It's a little harder to see how you do it on these other surfaces, but basically it works the same way. So these are surfaces because it takes 2 numbers to describe where we are. Now, and something that'll be important a little later, each of these surfaces, as I've drawn them, sits in three-dimensional space. And in three-dimensional space, they're a boundary of the inside. So in the case of the surface of the donut, we could have the donut or bagel itself, that solid object. That would be a three-dimensional object with boundary. The boundary is the surface. Those objects are called handle bodies or solid handle bodies. And we refer to distinguish between them, all we have to say is how many holes it has, and the technical term for the number of holes is called the genus, and we apply it both to the surface and the handle body. So the torus is a surface of genus 1, and it bounds this solid handle body of genus 1. Here's a 2-hole torus, a surface which bounds a solid 2-hole handle body, and so on. All right, now we come to a more difficult part of the talk. Surfaces are easy to see. How do we see the three-sphere? Well, in fact, you can't see the three-sphere. At least I don't know anybody who can see the three-sphere. And the reason is it does not exist as an object in our three-dimensional space. The only thing we have direct visual understanding of are the objects that sit in three-dimensional space, and then we can see them. Well, the three-sphere doesn't sit in three-dimensional space, just as the two-sphere doesn't sit in the plane or two-dimensional space. The two-sphere sits as an object in three-dimensional space, and the three-sphere sits as an object in four-dimensional space. But we can understand its properties by analogy with what's true for the two-sphere. So, how do we think about the two-sphere? One way to think about the two-sphere is through something called stereographic projection. So I'm imagining the sphere, this red sphere, sitting on this black plane, tangent or touching at one point, which I think of as the South Pole. And now I imagine a light at the North Pole, and I look at the shadows that that light would cast. So if I have a point on the sphere right here, the light ray coming from the North Pole would hit that point, and it would have a shadow on the plane. This identifies all the points in the sphere except the North Pole with all the points in the plane. And technically this is a topological equivalence between the sphere minus 1 point and the plane. Maybe the picture to keep in mind is you've got a ball of cheese that you want to give to somebody as a present. So you have to wrap it up. What do? You put it on silver paper. You wrap the silver paper around it and tie a bow. This is a little different. First of all, our paper is no longer a finite extent. It's the infinite plane. It goes on infinitely in all directions. And secondly, the way we wrap up doesn't leave any left over to tie the bow around. In fact, as you go out to infinity in the plane, you're just converging to this North Pole. So going out in any direction in the plane simply converges up toward the North Pole. Another way we can think about the sphere is a union of two disks. So I've started here with two copies of a flat disk, which I've separated a little bit. Think of bowing the upper one up a little bit and bowing the lower one down a little bit, continuing the bowing until they're semispheres, and then simply push them together in glue, and you have a copy of the two-sphere. So another way to think of the two-sphere is you can take two disks, two two-dimensional disks, glue their boundaries together entirely, but keeping the interior points separate, and what you'll end up with is topologically the sphere. Well, we do the same thing in dimension 3. No problem. So the three-sphere can be made by taking two solid three-dimensional balls now. So these are the solid objects whose boundary is the sphere. So I have two solid three-dimensional balls, and I simply glue their boundaries together entirely, keeping the interior points separate, just like I did for the disk. Easy, right? But you can't really see it. The other description, you can think of the three-sphere as the usual three-dimensional Euclidean space going on infinitely in all directions, plus one more point at infinity that would be identified with the North Pole of the three-dimensional sphere. Now that's the simplest of all three-dimensional spaces. And the others are made, there are many descriptions of other more complicated three-dimensional spaces, but for me today the representation I want to take is the following. You start with two solid handle bodies. Just a minute ago I started with two handle bodies of genus 0, the ball. But I could start now with two solid tori or two solid two-hole tori and glue their entire boundaries together, keeping the interior points separate. Well, if you had trouble visualizing how to glue the boundaries of two balls together, this is even more complicated. Nevertheless, it's a completely accurate mathematical description of the way you can make other three-dimensional spaces. And in fact, all three-dimensional spaces are made this way by taking some solid multi-hole torus of some genus, two copies of it, and gluing the boundaries together. This is called the handle body decomposition of the three space, and its genus is the genus of the handle bodies you've used in the construction. So try to indicate this with as good a picture as I can. So I go back to my two-hole torus. I'm now thinking of these solid objects. I have two of them, and I glue their boundaries together somehow. Now this time, it turns out, unlike the case of the sphere, there are lots of ways to glue these boundaries together, and you can get lots of different three-dimensional spaces by doing it. And that's part of the complication of three-dimensional topology. Nevertheless, that's how you make all three-dimensional manifolds. So as I've said, we've seen the example. The three-sphere can be obtained by gluing together two three balls. But when the handle bodies are more complicated than balls, there are lots of different ways to glue them together, and so you can get lots of different three-dimensional spaces from two copies of one solid handle body. Most of the attacks on the topological attacks on the Poincaré conjecture in the final analysis involved trying to take this handle body decomposition where we've used solid tori with lots of holes and somehow simplify the decomposition and use smaller, fewer solid handle bodies with fewer number of holes. If we get all the way down to no holes, that is see the manifold is obtained by gluing two disks together, we would have proved the Poincaré conjecture. So you somehow had to simplify this handle body decomposition. Well, that's what's proved to be intractable. So, as I indicated earlier, where I think Poincaré got his motivation for his problem was he was thinking by analogy with two dimensions where he understood everything. He was looking for some simple topological property that would characterize the three-sphere. So when I say characterize, I mean a property that the three-sphere has that no other of these three-dimensional shapes has. So if you have a three-dimensional space and you know it has this property, then you should be, according to the conjecture, able to conclude that it was the three-dimensional sphere. So what property should we take? Well, back to surfaces. Surfaces and loops. So I've drawn here the first three surfaces in our list. The sphere, which has no holes. The torus, that G equals 1 indicates it has one hole, G for genus. Here's a two-hole torus, and again, you're to imagine this list goes on and on. Well, let's think about a loop on the sphere. So there's a loop on the surface of the sphere. It's pretty clear that you can take this loop, and on the surface of the sphere, you can drag it and shrink it down to a point. When you do that, for example, the trace of that shrinking might look like this disk. You just shrink it down over that disk. This is true for this loop. It's not too hard to prove it's true for any loop on the sphere. For example, if I had the equator, that's another loop on the sphere, I could shrink it down to the North Pole just over the top, or shrink it down to the South Pole over the bottom. Well, the torus has on it a loop that you cannot shrink to a point. So if I take a loop that goes around this hole, no matter how I move it on the torus, it'll still always encompass or be caught up in this hole, and I'll never be able to continuously shrink it down to a point. And of course, on the two-hole torus, I can find lots of curves like that, loops like that. Here are two of them, one that goes around this hole, one that goes around that hole. Of course, there are others. There's an interesting that goes around the middle band, for example. There are these that go around the holes this way, and lots of others. But the point is that there's at least one. So on this surface, and then on all the other surfaces, there is at least one loop on the surface that cannot be continuously shrunk to a point. The sphere does not have such a loop. So this property, the property that every loop on the surface shrinks to a point, characterizes the two-dimensional sphere among all surfaces. Now, what about on the three-sphere? Well, the same argument that works for the two-sphere works for the three-sphere. If you have a loop in the three-sphere, you can shrink it to a point, continuously deform it to a point. Well, when I was a young graduate student, I learned every mathematical talk should have a proof in it, so here's your proof. We've seen the three-sphere minus a point is our Euclidean three-space. Well, this loop is going to miss a point, so we can think of it as a loop in three-dimensional space. And once it's a loop in three-dimensional space, it's obvious we can just shrink it down, say, to the origin of three-dimensional space. And here I've shown you how to do that. Here's a loop in three-dimensional space. You just pull it by straight lines down to the origin of three-dimensional space, and that's a shrinking of the loop to a point. And by our identification of three-dimensional space minus a point with the sphere, we can use this to shrink all loops on the three-sphere as well. So the three-sphere is a three-dimensional space with the same property that the two-sphere has, namely every loop on the three-sphere shrinks to a point. What about the converse? The converse statement is the Poincaré conjecture. The converse says if you have a three-dimensional space and every loop on it shrinks to a point, then your space is the three-sphere. That's the Poincaré conjecture. Intuitively, if your three-dimensional space doesn't have any holes that you can wrap a loop around, like the donut has a hole that you can wrap a loop around, if you don't have any holes like that, then your space must be the three-sphere. So technically, a three-dimensional space with the property that every loop in the space shrinks to a point is topologically equivalent to the three-sphere. This is almost verbatim what Poincaré said, at least in the language of his day. Why should we believe it's true? Why did Poincaré believe it's true? Well, it's not completely clear he did believe it's true. He didn't actually state it as a conjecture. He stated it as a question. And then he said, studying this question would take us too far afield. Well, one reason to believe it's true, Poincaré's motivation was, as we've just seen, the analogous statement is true for two spheres, distinguishing the two-sphere from all other surfaces. As far as I'm concerned, a much more important and powerful reason it's true came 80 years later with Thurston, 75 years later. When Thurston formulated his more general conjecture about three-dimensional spaces, the Poincaré conjecture was a very special case of that conjecture. And then he went on to establish his more general conjecture in certain special cases, unfortunately not a case that included the Poincaré conjecture. I think if you'd taken a poll of topologists when I first entered the subject in 68 or 70, my sense was they were split. As many would have voted for the Poincaré conjecture being true as would have voted for it to be false. If you asked the same question in 1985, I think you would have gotten 10-to-1 odds that it was true. And this is a strange psychological phenomenon because in the intervening 20 years, 18 years, there had been no advance on the Poincaré conjecture. But there had been advances on this more general conjecture, putting the Poincaré conjecture in a more general framework and seeing that that framework holds sometimes gave a lot of credence to the fact that it was true. And three-dimensional topologists since about that time have been working on three-dimensional spaces, attacking many other questions, assuming that the Poincaré conjecture is true. This does not come as a surprise to them. The fact that somebody's proved it and the way it was proved probably comes as a surprise. The fact that it's true doesn't shock anyone. All right, that's your lesson in topology. Now we switch to another field of mathematics, geometry, differential geometry, and in particular, Riemannian geometry. This is a slightly different subject, so bear with me. So any three-dimensional space, in fact, there's nothing special about three here, on any space of any dimension, one can put or impose a notion of structure, let's call it, a way to measure angles and lengths. So if you have a curve in your space, think of it as being parameterized by time, a particle moving in your space. There's a notion of what the velocity vector or tangent vector is at each point, and there's a notion then of how long the trajectory is. And if you have two of them and they meet at a point, there's a notion of the angle between them. That structure is called a Riemannian metric, after Riemann, who introduced it, or at least studied it. The problem with this idea, maybe it's not a problem, some see it as a gift, is that there are huge numbers of ways to put on these structures. And there's no obvious way to construct one that has some properties that you would like it to have. You decide ahead of time, I want it to have this, this, and this property. There's no obvious way to make one. And since you're working in technically what's an infinite dimensional space of possibilities, finding one is that with the properties you want isn't going to be easy either. So now I can tell you a little bit more about Thurston's more general conjecture. It says that any three-dimensional space admits an especially nice one of these Riemannian metrics. Now, in the brackets there, I've put, for all the mathematicians in the audience, the technically correct statement. You have to cut the thing in pieces in some canonical way, but let's not worry about that. This conjecture, in and of itself, as I indicated earlier, suggests a completely different approach to the Poincaré conjecture. Because here, the conclusion is not topological anymore. The conclusion is geometric. The conclusion is that there's a nice Riemannian metric. So we have a geometric conclusion instead of a topological conclusion. We might try to establish that conclusion by analytic differential geometric methods. And I believe that that insight was crucial to Hamilton as he was studying the Ricci flow. So Hamilton proposed a program to establish these conjectures, and if I can paraphrase it in this slide, in the following way. You start with any metric. Remember, we had no way to pick out a good one to begin with, and there were so many possibilities, it wasn't going to be reasonable to expect we could just pick a good one that we wanted. But heat it up. Heat the manifold up and let it cool. This is a euphemism, but let's go on. As it cools, the metric should distribute itself over the manifold homogeneously, just as heat in a metal bar will distribute itself homogeneously as it cools. And if it really distributes itself homogeneously over the manifold, in the end, we should find this nice metric, the one that we are looking for. So in a nutshell, that was Hamilton's idea. Notice if it works, it will establish not only the Poincaré conjecture, but also Thurston's more general conjecture, because it's going to produce these nice metrics in great generality. Well, cooling was a euphemism. So let me try to say a little bit more about what's really involved in Hamilton's equation, evolution equation. And to do that, I have to tell you about curvature. And let me try to illustrate curvature by the following phenomenon that I think we're all familiar with. If you have the top of an orange peel, about that much of it, and you put it down on the table, of course it will be bubbled up like this. If you squash it flat, it will tear. The reason that it has to tear is that there's not enough of the orange to cover the region in the plane. There's not enough stuff in the orange. More technically, if you look at the very top point of the orange and you look at the amount of stuff within within 1 unit of the top, that's our cap, you ask how much area do I have there, and compare that with the area of the unit disk in the plane, you will find you have less area in the orange peel than you do in the disk in the plane. So that's in the sense in which there isn't enough of it. This property that there's less area in the orange peel than there is in the corresponding region in the plane is an intrinsic property of the metric, the distance on the orange peel, and it's a reflection of the fact that the metric has positive curvature at this point. Actually, this curvature goes back to Gauss, and it's called the Gaussian curvature. So that's the simplest form of curvature. In higher dimensions, curvature is quite a bit more complicated. If you have a higher dimensional space, every two-dimensional direction has a curvature of the type I was just trying to describe. So you get a whole bunch of curvatures at each point in different directions, and they fit together into a complicated mathematical object that has the name of a four-tensor. But this object is intrinsically associated to the metric, and it's called the Riemannian curvature tensor after Riemann, who introduced it in the late 19th century, middle 19th century. Riemann went on to show that this is the only local property of your metric that's intrinsic to the metric. So, for example, Riemann showed if you have a small piece of an n-dimensional space and you can flatten it out onto a piece of the plane, then it has zero Riemannian curvature, and conversely, if it has zero Riemannian curvature, you can flatten it out onto the plane. So curvature captures is the intrinsic fundamental notion about the way metrics on spaces curve. Now that's not the curvature that directly enters into Hamilton's Ricci flow equation. There's a related simplified curvature called the Ricci curvature. It's exactly the same curvature that comes up in Einstein's equation. And it comes up for the same reason. So Hamilton's cooling process, what I called it before, is really the idea of letting the metric evolve by requiring it to change in time so that its time derivative is proportional to this curvature, this Ricci curvature. If you write this equation out in local coordinates on your space, you'll see that it looks very much like the heat equation, though it's nonlinear and it's a tensor equation instead of a scalar equation. Nonlinearity is very important because nonlinear equations, as is well known in the theory of partial differential equations, often, or almost always, develop singularities. And in fact, it was trying to understand these singularities and deal with them that was the hang-up in Hamilton's program for establishing these nice metrics. If you let your metric flow under Ricci flow, you hope it's going to go to a nice metric. Indeed, Hamilton proved under certain circumstances that really happens. But if you get hung up on these singularities, you're not going to be able to prove anything. But Hamilton did study this equation for 25 years. He established innumerable basic analytic properties of the equation in a solution. And as I just mentioned, he showed that in certain circumstances you could use it to produce the nice metric, for example, the metric you're looking for to prove the Poincaré conjecture. But we do face the issue of singularities. To really use Hamilton's program to give the topological result, you have to deal with the singularities. You have to analyze them and figure out how to continue the flow in spite of them. And that's what Perelman did. So in a series of 3 preprints in 2002-2003, I'm sorry I misspelled his name here, Grigory Perelman gave arguments showing how to deal with the singularities arising from Ricci flow and how to continue the process in something he called, or is called, Ricci flow with surgery. He then used this augmented flow, this Ricci flow with surgery, to prove the Poincaré conjecture. And he indicated in the second of his 3 preprints how to use the same technique to prove the general Thurston geometrization conjecture. If you're interested, here's a link, www.claymath.org, that will take you to Perelman's 3 preprints and also the 3 long manuscripts, the one that Tian and I wrote that weighs in at 473 pages. I hope you'll see that next summer on the summer reading beach table at your local library. There's an article weighing in at over 300 pages by Cao and Zhu, and an article on the archive by Kleiner and Lott, a lightweight at 200 pages. But what Perelman's preprints do and what these articles explain in much greater detail is a complete, comprehensive, correct argument for the Poincaré conjecture. And it's now been thoroughly checked. He has proved the Poincaré conjecture. And to me, what's as exciting as the fact that the Poincaré conjecture has been proved is that he did it using ideas and results from differential geometry and partial differential equations to solve this purely topological problem. Anytime one sees this sort of interaction between disparate fields of mathematics, it certainly makes me sit up and take notice and be very excited. What's its significance? Well, the obvious one, it brings to a conclusion the classification of 3-dimensional spaces. We've now solved this 100-year-old problem. And that's extremely satisfying and is a great victory for Perelman and also for mathematics. And as I just said, the interaction between the disparate fields makes the argument all the more interesting and important. But I think that in the significant impact in the future will be not on three-dimensional spaces, but rather applications of Ricci flow in other mathematical contexts. For example, it's obvious to try to apply this in 4 dimensions, and also to apply it to technically what are known as scalar manifolds or algebraic varieties. These should be the first applications to come. They're the closest to the three-dimensional questions. But then there's singularity development and other geometric evolution equations that are similar to the Ricci flow. For example, the mean curvature equation has many properties in common with this one. So other geometric flow equations, the way they develop singularities and how you treat these singularities, I think we'll see lots of advances there. And finally, and probably more speculatively, because I know nothing about applications of mathematics to physical processes, it is nevertheless true that many, many physical processes are described by the same kind of evolution equation, technically a parabolic differential equation, that the Ricci flow is, and understanding singularity development in those equations can have tremendous applications. We may look back in 100 years and see Perelman's treatment of the singularity of Ricci flows as the beginning of an understanding, much deeper understanding, of how singularities develop in these equations, how to handle them and treat them, having untold consequences for us in everyday life. But as I say, I'm not an applied mathematician, so take that with a grain of salt. Thank you.